on the wrong tab. Thanks a lot for your patience. So yes, my name is Maurizio Santora, and I am presenting here on behalf of my colleagues from Gamma Remote Sensing and the Max Planck Institute. And this is a study that we did using satellite data, radar satellite data, for the last 3 decades, and try to see if we can understand dynamics of biomass from it. This is in a nutshell, but now the scientific context of the presentation is the following. I mean, we are within the context of Earth system science. And if we want to understand how vegetation and climate will develop in the future, we need to have some data sets on which we can rely upon. And terrestrial carbon pool is a fundamental variable of these models. And if we look a little bit around what is available, we have some static data products or static information. And there have been some quantifications, like the paper in PNAS recently, that at least quantifies the amount of total biomass and its components, saying that woody above ground biomass is a very important component of the whole terrestrial carbon pool. Now, if we want to quantify the terrestrial carbon pool or the woody above ground biomass, actually, we would in first place rely on data from inventories. But we all know that these are sparse, both in space and in time. So if we want to understand the dynamics of biomass and also the spatial distribution, that gets quite complicated globally. We want to rely on Earth observation then for this, because we get a synoptic view of the Earth. But then the point is, well, no matter how you want to measure or see the Earth, no observation that we get is really related to the biomass, so to the organic mass, so neither to carbon. So we have to do some kind of extrapolation or infer from the measurements that we get from remote sensing to obtain some estimate of biomass. And now if we look a little bit into the literature, actually there isn't really a global data set of above ground biomass from remote sensing data. There's only one that extends over 2 decades. So there is a gap in knowledge about the spatial and temporal characteristics of biomass, forest biomass. And so it's difficult to inform Earth system models in a way that they can be driven a little bit, now I would say, better compared to the standard way of doing this with climate data, for example. So the aim of the study that I'm going to show you is, can we take another source of data from remote sensing that has been existing for the last 3 decades and quantify forest above ground biomass, so that we can then inform ecosystem models and do some additional work on carbon fluxes estimation. So what I'm going to talk about is data that is acquired from a scatterometer. A scatterometer is actually a radar, so it's an active system. You can always take measurements of the Earth, you're not impacted by clouds or darkness. And it really measures with high precision the measurement that it gets. In space, the resolution, however, is very coarse. We speak about 25 to 50 kilometers. And scatterometers have been used for decades actually to measure wind fields and wind speed. And over land, you may have heard about this when you are considering the estimation of soil moisture, for example. But in terms of land surface types and land surface dynamics, there has been very little use made of this. And so we're trying to move in a direction that wasn't really explored so far that much. So scatterometers actually have the great benefit of observing the Earth really many times. For example, you see here the example, that's a 3 days composite. So you can take a global view of the Earth every 3 days. And the thing is that if you take the so-called C-band, so wavelength of 6 centimeters, you have been having measurements since 1991. And nowadays they're operational and they will give you observations also in the future, because this METOP ASCAT that I'm showing you in the table, that's an operational satellite going to be used also in future decades. Now, the thing is, many people would say C-band, radar, 6 centimeters, what do you want to do with biomass? And actually this was one of the triggers almost 10 years ago to show that if you have one measurement, then you're not really related to any forest structural parameter or any forest parameter variable. If you start combining many measurements and then you do some kind of weighted averaging of estimates from biomass, then you can get much beyond what is expected from a single observation. And that's kind of strategy is used here again for the scatterometer data. Now, first of all, as I said, we are exploring a new type of data, so we want to see how reliable this might be. So what we did in this global study actually was to create an asset from LiDAR, spaceborne LiDAR. As I said, there is no global set of measurements of AGB, so you want to rely on some sort of vegetational structural parameter to understand if your measurement from the scatterometer is viable at all. So we derived actually measurements of, or estimates of canopy density and top of canopy height, which are displayed in the bottom here, from a set of 26 million valid footprints. And you can see that the distribution, spatial distribution of density and top of canopy height very much follows the kind of visual representation from the scatterometer. So there is some kind of information. But of course, we want to be quantitative. So what we did was to separate the measurements. Now this would be 1 day, so one observation, for the boreal, the temperate, the subtropical, and the tropical part. And we relate what is the so-called backscatter, so the observation from the scatterometer, to the product of canopy density and height. So vertical times horizontal property, a proxy for biomass, as you want to say, but we do not call it at all biomass. This is just important to realize. And we see that there is a relationship between the backscatter and this kind of biomass proxy. That varies in time. You see February, May, August, and November, in particular in the boreal and in the temperate zone. It's not a great sensitivity, but there is some sensitivity across the entire range of this proxy for biomass. I skip here because we are in the boreal conference, the part on the tropics. It's interesting to observe that even in the tropics, you have sensitivity across the entire range of values that are derived from the spaceborne LiDAR observations. So all of this is a knowledge that then we built upon in order to create what we call the Biomass framework. The Biomass, so biomass and scatterometer. And this flowchart actually summarizes a couple of concepts. We use this scatterometer, the data at the top. We use a lot of measurements. We feed it to a backscatter model, so no machine learning in this case. We use allometries that relate different elements of the scattering. And we do a weighted averaging of the daily estimates of biomass that we get from each image. So we try to maximize the information content on biomass in our final estimate as much as possible. So this is in a nutshell what we do, but important here in this context is actually to see what kind of results we may obtain. So we obtain from the whole bunch of observation at the moment, yearly maps of above ground biomass and the corresponding standard deviation as a measure of the uncertainty. And the standard deviation is obtained by propagating the uncertainty of each single element in our retrieval scheme. So the uncertainty of the observations, of the model parameters, and so forth. Everything is derived at 0.25 degrees, so roughly 25 kilometers on the ground at the equator. And these are the maps on the left, the map of biomass, and on the right-hand side, a relative standard deviation, so relative to the AGB. For those of you who know the distribution of above ground biomass, globally, that's a pretty reliable representation. And the standard deviation is about 30 to 40% of the value, or estimated value. So not a dramatically small value, but also not a dramatically high value. Now you may want to ask, how can I see if this result is valid or not? Well, we assembled a large database actually of plot measurements, and for each pixel, so 0.25 degree, we created an average of those plot values. Now, I know you would say, well, how can you compare a value representative of a 25 by 25 kilometer area with an average obtained over some plots? Well, that's something that we want to discuss. That's why actually I wrote here validation, but it's also a verification of the reliability. And actually, it doesn't look too bad, the distribution. We are particularly interested in the biasedness of the map. The boreal part is located below 150 megagrams per hectare, That's a global view. So the top part would be more for the tropics. But you can see for the boreal part, so if you're referring to the up to 150 tons per hectare, that's not bad. Okay. So the last 3 slides I want to show here are about the boreal zone. So now we concentrate on this part. And if we take the yearly maps and we take a global average for the boreal and polar zone, according to the FAO, we get a pretty constant value at about 55 megagrams per hectare. And if we also include now information on forest area from the CCI land cover by IIASA, which would be the red line, we would see that we are at about 75 petagrams of above ground live biomass in the boreal and polar zone. So not much of a change across the last 3 decades. And these are actually some first numbers that we are obtaining. If we now start splitting the dynamics in time, what I show you here is the so-called AGB rate. So we fit for each decade and for each pixel a linear function to the AGB estimates. And so the AGB rate will tell you how much AGB is changing linearly. So it's this slope of the linear fit. And you have it for the 90s, 2000, and the 10 decade. And we can see that there are different trends, both in space and in time. In the 90s, you can see immediately the result of the insect outbreak in West Canada. You can see the increase of biomass across the whole boreal zone, in particular in the 2000 decade, but also in the current decade. And that's something that we still need to understand exactly what happens in terms of spatial patterns. So for the last one that I would like to show you here, it's a biomass trend per country for Canada and Russia. I mean, we cannot get too small because of the resolution of the data, 25 kilometers. So in Canada, you see there was a decrease across the 90 decade and then a slow increase in time. This is, their counterpart is an increase of forest area and a decrease well, across the 2010, according to CCI land cover, so not our study. And if you combine the top plot and the middle plot, then you get that the total AGB in Canada, but also in Russia, more or less, was retrieved to be constant. We provide some first understanding of what is happening at a really core scale, but we need to get more understanding of this in the nearest future. And so, having said this, here we are more in terms of the novelty of the results. These are novel results that we see that we can quantify with this kind of measurement, the global AGB over 3 decades, so also in particular in the boreal zone. And in principle, we say that the system is operational, so we can add any year. AGB levels seem to be well captured, but of course the dynamics are difficult to verify because there is not enough measurements of biomass in time and over a large scale that can allow us to do something like this. We did it for the US actually, and it matched pretty nicely. The strength of our estimates is the temporal component. So to understand in which direction actually biomass tends to go. And there's a strong relationship also with canopy density estimates at coarse resolution. The maps, however, have their caveats, in particular where you have a fragmented landscape like in Europe, because there is a lot of components that affect your measurement. And so there we have to be careful when we interpret the measurements. But all in all, our message here is that this is a data stream which seems to be quite relevant to quantify the carbon pools, but it's important to combine these things with other, to reduce the uncertainties and reduce biases that we would observe, and also to go across scales in this 25 kilometers. And it would be nice also to see what happens if we work with higher density, with higher spatial resolution. So that was my talk, and I'm happy to take any question. Thank you very much.
Thank you, Maurizio. Very interesting presentation. Please, questions? I don't see anything.
Yeah, Dmitry, I'm sorry, Vyacheslav, but we might need to move on to the next presenters if we want to stay in time. We're gonna go over time for this session anyway. So yeah, let's try to keep in time. Vyacheslav, you're more than welcome to use the chat to write down your question. Thank you.
And then speakers can answer also in the chat. Okay, thank you, Helen. So then keep in time, please, Sergey Bartalev, next presentation.
We can see your slides.
Yeah, but not in a full mode.
And yeah, right. Yeah, okay, perfect.
Now fine. Sergey, you are muted. Sergey, we cannot hear you.
So I asked you to unmute. I don't know if you. So to unmute yourself, you have to go to the.
Yeah, now.
Okay.
Yes. Now should be okay.
Yeah. Now we can hear you.
Yeah, thank you. Sorry. So I'm representing Space Research Institute of Russian Academy of Sciences. So we are working in the big group within the project, which is focused on the estimation of carbon budget in Russian forests across the country. Sorry, it does not work. Strange. Sorry. Yeah. Okay. So to save time, I will not repeat everything, which is so you can read yourself from this slide. A lot of text. But in principle, so it's well known that the carbon budget in Russian forest has a significant level of uncertainties, and this is result of not very up-to-date information, considering large territory of Russian forest, the remote sensing became the only efficient tool for estimate properties of forest and the carbon budget for entire country. So to estimate the carbon budget, so we need a lot of different characteristics in the forest, including growing stock, species, age, productivity or site index, in other words. And of course, we need natural and anthropogenic disturbances as well as reforestation. So looking at this graph, this graph presenting the main concept of our approach. So besides of remote sensing, so we have very important component with ground samples, and so we include a lot of modeling with remote sensing data and ground data, because not all characteristics which we need we can derive directly from remote sensing data. So if you look at the top of my slide, so you can see the number of products which have to be retrieved produced for carbon estimation, and some of these products so we can derive directly from remote sensing, some of them so we can derive only by combining remote sensing data and models. So this is the logical scheme of our approach. So using the remote sensing data derived product like forest density or relative stock, so we can use one of these products, the growing stock volume, tree species, and forest disturbances, including fires and other biogenic disturbances. So all of these products we need in if you would like to estimate the carbon budget every year annually. So we need to have a possibility to update such products every year. So about models, so talking about models, we use well-known models, mainly developed by IIASA, International Applied Institute in Applied IIASA in Luxembourg, Austria, and developed by our colleagues and the co-authors, Anatoly Shvedenko and Dmitry Schepaschenko. And using remote sensing data together with models, so we estimate by comparison of directly derived from remote sensing data and models. So we estimate forest age site index. I will demonstrate how we do it. And again, they're using these characteristics like forest age, site index, the growing stock volume, tree species. We can evaluate different components of carbon budget, including the living part and the dead wood part. So we use, for the moment, we use MODIS 250 meters products. It's the long time series. It's only product which is homogeneously cover all country for about 20 years. And it's frequent enough to make a signal quite clear. It means to eliminate the clouds and other disturbing factors to derive surface properties, surface reflectance properties in time and in space. So they're using this product and our own, the approach and software, which I will not have time to present now. So we derive number of products every year from 2000 till 2020, and like land cover map, which 23 classes, and the 7 or 8 of these classes are related to forest. So you can see the legend here. You have the different forest classes, which are defined by LCCS land cover classification system. So, and for the talking about species, tree species, so we use quite frequent observation. This is a weekly clouds-free composites in the MODIS red band and the near infrared. And so we're using this, these curves are describing temporal changes of surface reflectance properties weekly, and you can see the difference between different species, which are used to classify the forest at the level of dominant species. This is a map of dominant forest species. It includes 12 main species in Russia. So another approach to estimate growing stock biomass is based on the link in the surface reflectance properties measured during the winter, because the background surface has a more homogeneous reflectance. You can see this the very high level of reflectance, the blue, this the white snow, and measuring the signal during the winter time. So we establish local, based on the species and very localized relationships between surface reflectance measurements and the biomass. And for the moment, the biomass we are using for biomass, we're using Biomass product, which is developed by Maurizio Santoro. So, and this is example of map for I think for year 2010, but we're doing this every year, and using these dynamic products with stock volume, growing stock volume, species, and land cover. So we are able to use the models to estimate other parameters which we need for carbon stock and carbon budget estimation. This is another example of estimation of forest height Again, so we use about 50 millions of ISAT2 LiDAR measurements for training, together with our classifiers, which use random forest regression, but localized, locally adaptive Lagman method. And again, the winter MODIS cloud-free image composites. And you can see the map, which estimate forest height up to even a little bit more than 25 meters. And on the right side, you can see the comparison of measurements of heights with remote sensing against the ground truth. So, and the correlation looks quite promising, and the RMSE is about 4 meters, which is also quite promising.
Sergey, 2 minutes.
Okay, so then we use forest disturbances, both fire and biogenic, to estimate fire severity and the level of measurement damages. And then using all of this data, we are able to measure total standing tree stock volume in time. You can see on the left top graph the dynamics of total volume in the forest. And then through modeling, so we derive from these measurements, we derived growing stock volume, I mean the living part, standing trees volume stock, and the fallen trees dead tree stock volume. And this gives possibility to estimate forest balance, the carbon balance. So this is approach how to estimate a site index and the age from dynamics of growing stock volume and the models. So this is based on the best fitting of real measurements with modeling. So this provide us opportunity to estimate the age and the site index. And this is a map of forest site index classes and age classes. So finally, so we estimated carbon stock in total forest biomass on the left graph, and the carbon balance in the total forest biomass on the right graph. You can see that the almost all period from 2004 till 2014, the Russian forest was acting as a sink, and sometimes with quite good sink. In 2007 was the best accumulation possibility of Russian forest. Unfortunately, due to fires and other disturbances, last year the Russian forest became slowly act as a moderate the carbon source. Thank you very much. Sorry for spending more of your time for my presentation. Yeah.
Thank you, Sergey. Very interesting presentation. One more results presenting dynamics in a Russian forest. And the next presentation will be mine, also talking about Russian forest. Please keep posting questions in the chat. I see already some questions and answers from Mauricio. So let me share my presentation. Can you see?
Yes,
it?
yes,
yeah.
you can see us. Yeah, presentation mode, perfect.
Yeah. So I am going to present here our research with a large group of people involved in this study, also authors of 2 previous presentations, also among co-authors of this study, and we have 10 institutions involved, and this study was recently published in scientific reports, and also got some critics and news coverage. Maybe you're aware about this. So a little bit about motivation. If you look at what Russia reporting to international organizations like Food Agriculture Organization or UNFCCC, you see almost no change in area and biomass over this 25 years from 1990 to 2015. But many studies shows actually that recent decays was quite good for Russian forest, and you can see some greening, increase tree cover, increase biomass, and so on. This discrepancy between official reporting and what we can see from remote sensing, it's because of Russia moved from one inventory system to another inventory system. It used to be a Soviet forest inventory and planning, or лесоустройство in Russian, but it's slowed down during last decades, and finally we have then more than 50% of Russian forest inventory more than 25 years ago. A new inventory system, more or less state-of-art NFI, just to finalize the first cycle. In our study, we use a portion of National Forest Inventory data and remote sensing data to receive a new estimation. You might know that remote sensing expert call our era, a coming era, as a gold era for forest and biomass observation, because quite a bit of satellites either already start observation or planned on the construction. Here is the list of some of them. In our study, we use product globe biomass map and CCI biomass map, and some auxiliary information like plant function type, vegetation map. As a ground data, we use collected at the forest observation system, where many institutions contributed with permanent forest plots. Which is recently published at Scientific Data. And here I would like to promote data sharing. If you measure something in the forest, please don't keep it for yourself only, but also you can share with many databases now collecting this data, and it's for mutual benefit. Analysis of global or regional analysis only possible if we put together efforts of different teams working on the ground. So finally, for this report, we got about 10,000 National Forest Inventory sample plots from 10 regions, it's in blue, and about 100 permanent research plots from forest observation system. They are distributed for all climate zones and more or less to forest types and regions over the Russia. We did some screening of the data because of, NFI plots just cover 0.05 hectares, while pixels we consider it's about half hectares. And also there are some discrepancies in time. For example, ground observation was in a year, and next year disturbances come, so forest loss, or sample plots was on the age of forest and not representative for the pixel. So we did some screening, and about 10% of data was taken away from this analysis. You can see there is some scattered between remote sensing and ground data, of course, and also some saturation between different remote sensing products, because different sensors used to produce them. we try to fit different models, and finally, surprisingly, the linear models was working the best in our case. But of course, it was not just one model for entire country, but for different tree species group and climatic zone and even region use separate models. Yeah, finally, here the scatter plots predicted versus ground data. Still some scattered, you see, but if you aggregate data to the administrative region, you have quite good estimation of biomass, and also you don't see any systematic error, any bias. So if at pixel level, we can observe sometimes error over 100%, then at administrative province level, you already have 1.6% in average. At the country level, less than 1% error. We produce a map at the about half-hectare resolution, and also GSV estimation and standard error. But we prefer to use aggregated data for at the regions. Then you are not you are at the safe side when you're talking about biomass at regional level. We pointed our product for the year 2014 because it's median year for remote sensing products we use and for ground data used. So if we take the last Soviet Union report on forest 1988, then you can see the changes which is happening during this several decades. Of course, our critics are saying that we compare apples to oranges because the different methods used, but there is some proofs that in the year 1988 there is no big systematic errors, or at least we corrected the systematic error, and also for the year 2014 there is no systematic error. However, these results need to be treated with a careful but interesting result that in the area where we have enough precipitation, we have the largest increase of forest productivity. When we have at least climate change, like in West Siberia, we have least changing in biomass. Also, in our paper, we listed several issues with this analysis. So we're quite sure about estimation for the year around 2014, because large amount of ground data use. In our paper, we included both data and also code. So all results reproducible. But of course, comparison with 1988 is a little bit more questionable. So here is a blob slide is asked for this conference. Our methodology, we calibrated global remote sensing data with ground data, NFI, and forest observation system, and use as a reference Soviet Union inventory report. And main finding is that we found 40% more growing stock volume in Russia than it's reported in national reports to UNFCCC and to FAO. Thank you for your attention.
Thank you, Dmitry. I think we have a couple of minutes for questions for Dmitry. Suzanne.
Hi, very nice presentation. Can you hear me?
Yes. Yeah.
Okay, I'm just curious why there's such a small amount of ground data shown on your map for the central part of Siberia.
Yeah, at the moment we analyze the data from Krasnoyarsk region, which is a central Siberia. There was not available yet data, not pre-processed. The first cycle of National Forest Inventory in Russia just finished in 2020, and still we don't have official results from NFI yet.
Thank you.
Yeah, please. Yeah, I would like to highlight this efforts of many people and many institutions, and I hope it will promote a little bit sharing NFI data from Russia for not only for our but for different studies, also including what is Sergey Bartalev is doing with his lab and so on. Thank you.
Any additional questions for Dmitry or for Sergey? If not, but then Dmitry, I'll give you the floor again.
Mm-hmm. Thank you for your attention. That's good if we have 1 minute saved. Then we have next presentation, but by Tina Mayasalmi. Thank you. Thank you, Tita. Very interesting presentation. Please, do we have questions? Okay, please, if you, I don't see hands, but you still can put your question if you have one in the chat box. So now we will have 3 poster presentations, which we will be quickly presented here. The first one is, please, Elizabeth Hoy will tell us about NASA Above Airborne campaign.
Hi, can you guys hear me?
Yeah. Just
okay, great.
in present mode, if you turn your slides.
Yeah. There we go. Oh,
yeah, super.
You're seeing the whole thing. Okay, great. Well, thank you. I'm Liz Hoy, and I'm with the NASA Above Airborne campaign. I work at NASA Goddard, and I'm going to leave my video off because I don't have great bandwidth where I am right now. So many of you have probably already heard of Above. It's a large-scale NASA-led study of environmental change in Arctic and boreal regions, and it's focused on the resilience and vulnerability of ecosystems and society to environmental change. So part of what we're doing in Above, and all of this is on my poster, we have this framework of vulnerability and resilience that has been developed to think about the drivers and impacts, consequences, and responses of change and to change. And then, of course, since this is something that NASA is doing, NASA really likes to have these kind of studies where you're looking at things from the plot level all the way up to the orbital and modeling level. So during the 10-year campaign, we're making observations at the plot level, tower level, airborne, orbital scale, and then we're using this information in our integrated modeling framework. So the Above Airborne campaign really had these goals to provide this domain-wide context based on site level processes, and to link satellite remote sensing to what we see on the ground, and then to demonstrate new remote sensing technologies and multi-sensor data analyses. So on the map on the left, you can see just a snapshot of all of the different places that we've been over the years that we've done the airborne campaign. So starting in 2017, we did many flights. We had, I think, 8 or 9 aircraft out taking measurements related to, we had radar measurements, we had hyperspectral measurements, LiDAR measurements, looking at hydrology, permafrost, fire disturbance, many of our science themes for the campaign. Then we also did more flights again in 2018, and then we did some additional flights in 2019. 2018 and 19 had less flights. We mostly focused on the L-band SAR in in 2018-19, the ABRIS data, excuse me, which is a hyperspectral imagery. And then we did Elvis imagery in 2019, which is a LiDAR imagery. And then in 2020 and 2021, we were supposed to have some airborne flights, but of course the COVID-19 pandemic really forced us to postpone those measurements. And so we hope to go again in 2022, which will link nicely to another above campaign called SNOWX, which is supposed to take some more winter measurements. And I've just given a sampling here of some products that are available based on the above airborne campaign and some links, which you can find on the poster as well. So you can find information at the Oak Ridge National Labs Distributed Active Archive Center, the ORNL DAC, which is where we have a lot of our above data. And then also you can search for all above NASA funded above data at this Earth Data Search portal. And I've just shown here using on the left, we're looking at active layer thickness from LMP band SAR data. And on the right, it's just a high resolution hyperspectral image of a watershed on the Seward Peninsula. And then I just wanted to give a brief announcement that there's a new funding opportunity out for the above program. So it's the Terrestrial Ecology Phase 3 announcement was just posted on, I think Monday. So I'm happy to say that it's out, and you can see the link at the bottom for more information, or of course, go to the NASA website as well. The notice of intent is due September 15th, and proposals are due November 17th. And that is it for me. I know I only had a few minutes.
Mm-hmm. Thank you. Very interesting presentation about above project. Is it from 2017 to 19 or started earlier?
Yeah, so the whole campaign will go for another few years yet. So this phase 3, which was just, as the solicitation was just put out, is for more another three years or so of work, and this will include less of a field component and more of kind of a modeling integration component, but we still plan to have some airborne measurements and then maybe some additional field work.
Okay, I see. Thank you. Any question? Okay, I don't see raised hand. Keep posting. I see
Thank
some.
you very much.
Yeah, thank you, Elizabeth. So I see that people are using chat box for question and answers, which is good. Okay, next poster presentation, short presentation by Alexey Panov, please.
Okay, wait a second. Can you hear me?
Yeah, we can hear you.
Wait. Then it should be, yep.
Okay.
So, then one. Can you see?
Yes,
yeah,
can
but
see
not in full screen.
Very good, very good.
Yeah.
I am sorry that it's quite not big one. Good evening, dear colleagues, and I am Alexey Panov and representing Institute of Forest in Krasnoyarsk, Siberia. And now let me move you to the north and very briefly introduce our trace gaze observations that are conducted in the Siberian Arctic. The study area is the Gulf of the Yenisei River, one of the major rivers in Siberia and located in the Taimyr Peninsula. The recently established atmospheric observation station is deployed on the edge of the Dixon settlement. We see it on a map. And the station is operational since 2018 by joint efforts of Institute of Forest and Max Planck Institute for Biogeochemistry in Germany. The instrument on the top includes the Picaro analyzer you see on the screen that continuously measures atmospheric mole fractions of carbon dioxide, methane, and water vapor in the air that is pumped at 30 meters above ground level. You see our meteorological mast, and additional sensors are used for meteorological records. The seasonal footprint for the site implies pristine air coming from the Arctic Ocean in late spring and summer, while observation during frost period may be more receptive to the continental part of northwestern Siberia, you see in winter and fall. Here we present some results of the first years of our measurements. The CO2 amplitude, I go to the results section. The CO2 amplitude, so the difference between winter maximum and summer minimum levels, is higher than the values reported for Ambarchik, Tixi, and K. Baranov observatories, the other Arctic stations in Siberia. But this can be attributed to the oceanic influence in summer, with the input of CO2, depleted air, rather than continental sinks. On the right side of the results section, you see the synoptic variations of trace gases that we produced after decomposition of time series, and these fluctuations reflect local sources and sinks in study area, and they arranged according to 4 geographical domains. In general, we found out that the negative carbon dioxide signatures from the Arctic oceans are observed in spring and fall, and achieving positive values in summer. The methane signatures are slightly negative over the continent and much lower value recorded in the Arctic Ocean, assuming stronger depletion of methane over the ocean. And within the continent, the eastern and pristine domain shows lower negative methane values, while in the southern and polluted domain, even positive signals are observed, assuming larger methane sources on the source compared to the eastern part of the Taimyr Peninsula. This is it, should be 2 minutes, and thanks for your time. I'm ready for questions and comments in the chat. Thank you so much.
Thank you, Alexey. Interesting presentation. So you measure something, and we need these measurements, of course. I don't see a raised hand, so please check message box for the questions. So next short presentation will be from Siddhartha Khare about black spruce phenology, please.
Hello.
So, yeah, just let me, Dmitry, from the email I sent you yesterday, Siddhartha will give a full-length presentation.
Yeah, right, sorry.
Yeah.
Mm-hmm. Yeah, please.
Yeah. So can you see the presentation?
Yes.
Yep.
So I'm Siddhartha Khare, and I'm currently postdoctoral fellow at McGill University. And this research was funded previously in my previous research lab at University of Quebec at Chicoutimi and Ministry of Wildlife Park, Quebec. So the topic is calibrating black spruce phenology observation with satellite and Pheno Cam time series data. So this is the outline of my presentation. I will start with a problem statement, then satellite and Pheno Cam data basics, and then methods, and then result analysis, and finally end up with the conclusion. So we all are aware that Quebec boreal forest is basically, it is covering like more than half of its territory is covered by one of the largest forest reservoir in the world, and it is accounting for 20% of the total Canadian forest and 2% of the world's forest. So forests cover more than half Quebec's territory, nearly 900,000 kilometers, and which is about twice the size of Sweden. And the forest management in Quebec is governed by rigorous legislative and regulatory framework. So here the annual temperature basically it ranges between -4 to 1.1 degrees centigrade, and the absolute minima you can understand here it is close to -47 degrees Celsius, and this area also experienced a lot of snow, and the frost free days is almost like in between 67 to 106, and a lot of remote areas and limited accessibility because of the bigger area, and the repeated measurements are not possible if you go to the ground, and various quick events, storms, and other events happens. That's why it's very, very difficult to take the data set on a regular time interval. So it was important to understand the phenology of this area, and how to understand phenology basically by using different parameters, like which understand the biological events on a seasonal basis, which includes like chlorophyll concentration, pigmentation, photosynthetic activity, bud swelling and apical growth, and leafing and leaf senescence. But the problem in this area is that the tree species which I'm focusing right now is the black spruce. So the problem is the evergreen. So basically, why I'm saying the problem, because evergreen species generally retain their needles for several years, and older needles that gradually drops off after a number of years, that depends on the species. This characteristics of evergreen species prevents a clear and easy identification of needle and canopy development. So the critical assessment and the calibration of Pheno Cam chronologies based on field observation of phenology are therefore essential for verifying plant phenology, but such calibration is still scarce, mainly for conifers. And the aim is to calibrate satellite and Pheno Cam time series data using the field observation for the understanding of bud phenology, which we have collected in the southern side of the Quebec. So we collected the phenological data where we have 105 black spruce saplings, which is almost 6 years old, and this plantation in the southern border of the boreal forest. And we have taken the weekly observation in between April to October for the year 2015, 17, and 18. These are the sites of these young like the black spruce saplings, and we were collecting the data on a weekly basis. And then the different stages that we have calculated based upon this field observation data, which started from the bud break to the bud set, and where how the needles basically coming out and how it is the flowering is taking place. So we all are aware that we have various time series and high resolution and low coarse resolution data set available from the remote sensing perspective, and MODIS is available from last 19 years, and it is free. Similarly, Landsat is also available from last 30 plus years. So in this case, basically, I have taken the data set of MODIS to understand the time series analysis of black spruce data, and then we have calibrated with the help of field observation data. Now, just a small introduction about the Pheno Cam network. So there are various Pheno Cam towers which are available across the North America and some of them in Europe also, and they take the direct observation of the tree or any species. So you can mount on the tower, and then it will directly take the observation, and you can get the time series images at every 15-minute interval of time. So this could provide a long-term phenological observatory, and this started in 2008. So this technology is now more than 10 years old. Now this is the special distribution of different Pheno Cam towers in the Northern American continent, and the area which I'm focusing is the Simcoe, is the southern forest, southern site in the Quebec boreal region. So this image is showing the time series images of every day. Like we collected and then we combined all these images for creating the GIF. Now this is the Pheno Cam network, and out of that, this is a tower, and we have collected data for different years. And in this case, we are showing the analysis of 15, 17, and year 2018 as 3 years. So we have used two different indices, GCC and NDVI. The first one is green chromatic coordinate index, and second one is normalized difference vegetation index. So this one is basically we have derived by using the Pheno Cam, because in Pheno Cam we have RGB camera. So we have used the advantage of this RGB camera, where we use this digital number of RGB filters, and then we calculated the GCC, that is called green coordinate chromatic index, which uses the combination of green, red, and blue channels. But in the case of NDVI, which we have modest data available, so it uses the spectral reflectance data of near infrared and the red band correspondingly. Now the fitting, basically we are using the time series data. So the fitting is very important. So we have used the double logistic approach, where we have calculated the start of season and end of season. And in between this time period, we have calculated the different phases of bud, and then we calibrated by using our field observations data. So the calibration method, basically it includes the two approach, like the punctual sequential events and the continuous curve. So the continuous curve that we have obtained by using the time series GCC and NDVI data, and the events that we have observed on the field, and by combine them, and then we use the logistic approach in the SAS by using the ordinal logit models, and then we calibrated our observations by the help of remote sensing data. So the first one, the result I'm showing is the calibration using the satellite remote sensing data. So in this case, this is the site where we have the field observation, and then we have used the forest inventory data of the MFFP, and then we have taken the 5,000 black spruce stands, and in these they're covering the significant portion of the Quebec, and then we have used this calibration approach in order to specialize this information across the significant portion of the Quebec. So we have used this double logistic approach, which I have shown you earlier as well. And then by using this double logistic approach, we have estimated the beginning and ending period of the phenology. And then by using this, we have calibrated and then specialized this information across the significant portion of the Quebec for these 5,000 pure black spruce stands, starting from 2009 to 2018. And then this different hotspots, basically we have generated, which represent the bud break and bud set starting from 2008 to 2019. We had this data 2015, 17, and 18 field observation data. So for these field observation data, we have plotted this time series data of NDVI along the year. And in this case, this annual NDVI basically showed a well-shaped pattern with a slow increase in spring and followed a rapid increase in culmination in July and a decrease in autumn until it reaches a minimum value in the winter. And the double logistic function basically it represents the NDVI well during the whole season, including the asymmetry in the transition between spring, summer, and autumn. And the dates of bud break were not homogeneous across the study area. It generally occurred in the southern region, end of April to May, and later in the northeastern region, mid of June, with the larger variation observed along the longitudinal gradient. And the spatial pattern of bud set in this case was not constant and has no clear trend could be found among years. And late bud set occurred more frequently in the western region. So that's how we represented the beginning and the ending of the bud break and bud set for the significant portion of the Quebec by calibrating the remote sensing data with the help of field observation data. And when we calibrated the Pheno Cam, so it's a kind of direct observation because the tower is standing in front of it, and you can take the direct observation. And we have taken the images on a daily basis. We removed those images which are having some haze problem or the snow problem, larger snow on the trees. So we removed those images, and then we have similarly we have plotted the NDV like GCC. In this case, we calculated the green chromatic coordinate index. So we plotted the GCC for 2015, 17, and 18. And here we have used the digital camera NetCam Excel, and each 30-minute images were there, and we took one image per day. And again, the double logistic function was used for the fitting of this. And then basically we calibrated our information by using the Pheno Cam. So basically it is more direct compared to the remote sensing, because remote sensing is the spatial resolution is 250 meter, but in this case the data set is currently like available directly in front of the trees. So in the GCC also showed the well shaped pattern with a slow increase in the spring, followed a rapid increase and then culmination in July, and gradually decreasing in autumn and winter until the reaches the minimum value. And that's how basically the beginning of bud burst or bud break, I should say, was observed in mid-May for both NDVI and GCC, when their values reaches to 80.5% and 72% of its maximum amplitude. And then when we compare the result of GCC and NDVI, then in that case, this is the observation calculated in the field. And then this is the calibration that we have done for the standardized GCC and the standardized NDVI for different phases like bud break and bud set phases. So in this case, on average, the process of bud burst begins in the mid-May and it ended in mid-June. Overall, the process lasted approximately for 20 to 27 days, depending upon the year. And in this case, the bud set started at the beginning of July and ended at the beginning of September. The standard deviation between years during bud set phases was larger than in bud burst phases in this case, and GCC increased during the whole bud burst process, including the part of bud set. And in case of like NDVI, the large standard deviation was observed for bud burst compared to this bud set. So that's how we can see the difference between the NDVI and GCC derived phenology, and when we calibrated for this. And these are my conclusions. So we know that okay, satellite based NDVI and Pheno Cam based GCC values represent reliable threshold, indicating the boundaries for the growing period. And basically our study bridge between the field observation and satellite and near surface remote sensing data, and near surface remote sensing data can be used as a very good calibration also for the remote sensing data also, because this is more direct compared to the satellite data, and it provides a statistical sound protocol for reliable timings of bud phenological events using calibrated GCC and NDVI time series data. And this approach can be very, very helpful for the wide areas in the Northern American continent, especially because we have so much abundance of the Pheno Cam network in the Northern American continent. So thank you. So these are this result were published in two different papers. One is in the remote sensing, where we have calibrated the remote sensing observations, and the second one is the Pheno Cam observations. So one is in Canadian Journal Remote Sensing, and the other is in remote sensing. Thank you.
Thank you. Thank you. Very interesting presentation. And also Good shows us network, global network already collecting this Pheno Cam data. I'm wondering if it's same equipment everywhere and how expensive this equipment.
This equipment, see the Pheno Cam camera, it costs around $5,000 to $6,000. But you need a data logger, and if you want the tower in the remote areas, and the cost of technician, it will cost you around like $15,000 in establishing the one Pheno Cam tower.
I see. So I see Vyacheslav Haruk wants to ask question, please.
Thank you. May I ask you, what do you know about phenological changes throughout the Canada, or particularly in your study area? How it's shifted now to earlier or later dates?
So it means, if I understood your question correctly, so you're asking the phenological changes in the area where I'm working currently?
Do you observe narrow changes in the spruce phenology?
Yeah, that was a challenging part, because with the satellite we are able to clearly understand the seasonal pattern in the spring, but the autumn phenology was not clearly distinguishable. But in the case of Pheno Cam, because it is more direct, so we got the spring phenology more accurate when we compared with our field observations. And in the case of autumn also, the field observations were more comparable, and more higher correlation was there in case of Pheno Cam. But in case of satellite data, in autumn phenology was not very much clear.
Okay, thank you.
Thank you. Then we will move to the next presentation by Ranjit Gopalakrishnan. I apologize if I am not correctly pronounce the name.
Yeah, we can hear you, Ranjit.
Okay, that's good. Just go for the.
Yes, we can see your screen, your slides. No, your screen. Yeah, and then. Yes, but. Okay.
Yeah, I guess it's all good now. Okay. So hi, my name is Ranjit Gopalakrishnan, and I am a postdoc at the University of Eastern Finland, the School of Forest Science. And basically my talk today will be about using a large set of forest plots to validate a physically based radiative transfer model, like the FRT radiative transfer model. So, quick introduction about FRT, 2 slides. So FRT is actually the forest reflectance and transmittance model. It's basically a forest reflectance model. So basically it's a physical, a model which simulates the physics, or the physical transfer of radiation from the sun to, when it interacts with the forest canopy, and then when it reaches your sensor, typically a satellite sensor. Basically the forest canopy is split up into, various elements like crowns, trunks, and things like that. And some of these elements, you can see, they are modeled as geometric objects. For example, crowns are modeled in this picture as, ellipsoids and such. So yeah, this model was introduced way back in 1991. So it has been around for almost 30 years. And so the latest version that we are using is kind of using, has been developed over 30 years. So, and it has been validated in this radiation model intercomparison exercise, which was, there has been various rounds of it. And the last one was in around 10 years, before 10 years, around 2010. And then there were like 12 models participating. And so there has been some level of validation. And it is widely applied in the boreal region. And yeah, I guess some more details. You can see that, it has like various components. So there is a separate computation component for the highly directional first order scattering. And then there is another component for the higher order scattering, so that, you kind of get a resolution of the scattering events. And then there are some, optimization, so that computations are done faster. So there is a statistical modeling of some components, and then there is other optimizations. And again, why are models such as FRT important? Especially in the context of remote sensing. So these models are important because, they help us understand satellite observations better. So when we get a set of observations, or for example, surface reflectance or something like that. So it's always good if we understand why certain observations were of certain value, and things like that. So these models also help us estimate vegetation characteristics in remote locations where, there are no field plots. So this is typically done by inverting the model against the measurements. And then, one very important role in the context of, climate change is to better understand Earth's radiation budget, because as you all know, land surface albedo is a big component in climate change, especially in the boreal region. And also it's a big, it's one of the biggest uncertainties when it comes to land models. So yeah, why this particular exercise is important with respect to FRT validation is that previously, for example, I talked about the RAMI intercomparison and validation studies, but in those exercises, the validation was only done for a limited set of forest plots and forest stands, for example, homogeneous forest stands. And this study that we have done tries to extend that validation to a much more wider, more heterogeneous set of forest plots. So yeah, the reference data that we used in this study is the Landsat 8 surface reflectance product. So this is based on the Landsat 8, which was launched in 2013, and high quality instrument. And then because of its short revisit frequency, it's like once in every 16 days. So approximately 23 images over a spot per year. So there is it provides us a large database of images to work with, and it's a fairly high resolution satellite, and then and it has been well validated. So you can see that the surface, the accuracy of surface reflectance is 0.001 units. And yeah, I just wanted to clarify before we go further that the variable of interest in this study will be the bidirectional reflectance factor, or the BRF. So yeah, so let's quickly look at the methodology. So for this study, we have concentrated on the region of southern Finland. So this is mainly because of the for the northern Finland region. And we have a number of field plots from the Finnish Forest Center. So for any given forest plot, what we do is that we try to identify Landsat images which were acquired within a plus or minus or within a time window of 6 months from the date of plot measurement. And so we have typically like 10 or 12 Landsat images, cloud-free Landsat images. And then for each image, I should say for each pair of plots and image, we do a FRT simulation where we simulate the bidirectional reflectance factor, and then we compare it to the Landsat bidirectional reflectance factor. And by this process, we were able to get a really huge set of, pairs to work with. So which again talks about the, kind of usefulness of Landsat. And yeah, so, this is like a very, this is an overview of the results. Cannot go into them at more detail, but then, so this is a scatter plot. This is a set of scatter plots where you have the FRT simulated reflectances on the y-axis, and then the Landsat observed reflectances on the x-axis. And then you can see that the species or the dominant species of the plot up here is pine, spruce, and birch. And of course, the band, the Landsat band is like red and near infrared, NIR is also given. And then one thing that you can see is that FRT tends to overestimate for a lot of cases. And another thing you can see is that the colors basically represent the maturity of the plots. So the total volume in terms of timber. So the red color represents low volume, that is like seedlings and saplings plots, and the green color or the dark green color represents the highest volume class. That's basically mature plots. And so you can see that the seedlings are not so well simulated, but then for the mature plots, especially for the pine and spruce mature plots, you see that they are very near the 1:1 line. So yeah, this is just to make things more quantitative. So I had calculated the RMSEs associated with this set of 6 plots. So you can see them highlighted in this part, the black rectangle, inside the black rectangle. And just wanted to point out that these RMSEs of 0.01 are considered like really good because climate models are supposed to have a sensitivity of 0.02 units. And the RAMI exercise had brought out RMSEs of 0.01 units. So, so the main point is that FRT is very effective in some forest stands and for some bands, but maybe not for the other bands. So, so this is a set of seasonal trends. So the May to October is the snow-free period in Finland mostly. So in this exercise, we just concentrated on the snow-free period. And what I'd like to point out at this point is, if you observe the blue lines, so the blue lines are the plots where the total volume is greater than 100. So basically the mature plots. And of course, these are the months. This is May, and of course 10 is October. And you can see that the blue lines are kind of coinciding in many plots. So So what we infer is that FRT is able to simulate the seasonal trends too, in some cases. Okay, so we did some more involved error modeling. We used linear models, and so of course the bias or the error was the dependent variable, and then we looked at a number of independent variables, and then we found out that we could explain the mean bias and the variances in bias by various factors. So to conclude, yeah, Landsat 8 surface reflectant products provide a large validation data set, so thousands and thousands of plots. And then we have seen that FRT shows good potential in certain forest types, but there is of course a potential for improvement in other forest types. And yeah, various factors influence FRT efficacy, and some of them are listed here. And then of course, because we know we can model error, it is also possible to bias correct FRT to a certain extent using these variables. And then you know, so we are in communication with the model developers, and we hope we are sure that these results will be useful in revising the model further. Okay, thank you.
Thank you very much. Yeah. So I don't see raised hand, so keep posting questions in the chat box. We move to the next presentation. Please, Hans-Erik Andersen, floor is yours.
Okay, let's see here. Can you hear me okay?
Yes, yes, we can
okay.
hear you.
There's a second here. Okay, hopefully you can see my screen.
It's coming up. It's coming up.
Okay, okay.
Yes, we can see your screen. And
okay. Okay, well, good morning. Yeah, so I'd like to talk to you this morning for a few minutes. First of all, Hans-Erik Andersen, I'm from the U.S. Forest Service Pacific Northwest Research Station. And I'll be talking to you about kind of giving an overview and then I guess a discussion of some of the remaining challenges in implementing our American NFI, what we call FIA, Forest Inventory Analysis, in the boreal forests of interior Alaska. So just kind of an overview of the interior Alaska FIA inventory. So where you see FIA, just think NFI. So in terms of the information that we're hoping to get from this FIA inventory in interior Alaska, of course, kind of basic information. We're mandated by the U.S. Congress to provide summary information related to forest resources over every state, the forested areas in every state in the country. So that's sort of a primary kind of mandate for the inventory. The amount of forests in interior Alaska are significant. We estimate that there's about 47 million hectares of forest. So what I call interior Alaska is the area delineated by black on the left in this graphic. It's about a fifth. We estimate it's about a fifth of U.S. forest land. So it's not an insignificant amount, amount of forest in interior Alaska. Of course, there are a variety, and this has been well documented in this conference already. But there's a variety of significant kind of disturbance factors that influence the ecological dynamics in this forest system, including permafrost degradation, obviously fires, as well as insect outbreaks and infestations that create widespread forest mortality. And of course, there's a large number of small rural communities distributed throughout this area that are quite interested in being able to use the local biomass resources for their heating and energy needs, and to reduce reliance on diesel fuel for heating and power. These are also largely subsistence economies in these local communities. They rely upon largely, hunting and fishing of the local resources to get by, and so there's a keen interest in habitat quality throughout this region. And of course, at the end of the day, we would like to be able to use the inventory data to kind of yard up the information related to carbon dynamics and report that at both the national and international levels. So this was the original plan for the Interior Alaska FI inventory. So it was basically a systematic grid. This is the systematic grid of plots only on forested land. The sampling intensity was about 1 plot per 12,000 hectares. It was expected to be about a 15-year inventory completed in 2028. These are large areas, at least by our standards in the US. I mean, we divided this area up into 6 inventory units. Each one of these inventory units is about the size of a large state in the lower 48. You can see the areas there. We are collecting additional measurements on these plots to better characterize the boreal forest conditions. So these are measurements that aren't necessarily collected elsewhere in the US, or at least in the same way. So we are collecting a soil sample. This was talked about yesterday in Sean Cahoon's poster presentation. We're also collecting a larger sample of small trees. We are collecting additional measurements on lichens, mosses, as well as tree cores. And we are collecting better GPS spatial coordinates using high precision GPS on our coordinates as well. One challenge of implementing the inventory in this area is the extreme logistics and the high costs involved in establishing these plots in very remote, largely unroaded areas. Almost every plot in Interior Alaska is only accessible by helicopter, which you can imagine is extremely expensive. Because we are now moving into Western Alaska, which this shows the road network in blue, which is largely unroaded, virtually no transportation network. The inventory is getting much more expensive. So we are kind of looking at potentially modifying the inventory design in Western and Northern Alaska to increase due to these increasing costs and the logistical complexity. And I'll talk a little bit more about that in a few slides. So in order to kind of increase the statistical efficiency of our inventory, we actually are working closely with scientists at NASA Goddard Space Flight Center who have partnered with us to collect state-of-the-art high-resolution airborne remote sensing with a multi-sensor instrument over all of our FIA plots, as well as kind of along these strip samples covering each inventory unit. So the system's called the G-LIGHT system, or Goddard LiDAR Hyperspectral and Thermal System. It consists of a laser scanner. So obviously we're getting detailed terrain information from that laser scanner. We're also getting canopy height information from the LiDAR. It also has a hyperspectral image sensor. So we're getting very 1 meter resolution, high resolution hyperspectral information. And then they've actually recently added a very high resolution stereo or camera that's collecting stereo imagery at about 3 centimeter resolution as well. It also has a thermal sensor that's there, but we haven't kind of dug into that data yet. So in order to use the hyperspectral information, they are also providing about 44 hyperspectral vegetation indices, and these are the data that we basically use, or the metrics that we use in our modeling. So how to integrate this G-LIGHT information with our kind of standard inventory estimation processes? Well, I'll focus on the Tanana, the first inventory unit that we took on, the Tanana inventory unit, which was the field inventory was completed in 3 field seasons, 2014, 2016 to 18. They established about 1,100 FIA plots in this area. About 822 of them are forested at a cost of about $7 million US. NASA Goddard flew 60 G-LIGHT strips over covering every FIA field plot. at a cost of about $500,000 US. So that the G-Light sampling constituted about 7% of the total inventory cost. This shows the, oh, sorry, I should back up if I can, this might be a mistake, but okay. The graphic in the upper left shows the field plots in green, and then the red lines are the G-Light strips. So in terms of the different estimators that we are comparing in this is just, so we used kind of the standard FIA estimation, post-stratified estimators that are well documented in what we call the green book, it's just shown here in the upper right. So a standard post-stratified estimator that uses basically a kind of a wall-to-wall classification, forest cover classification as the basis for post-stratification to provide sort of weighting to the plots to increase the precision. This is just the estimator itself on top, and then the variance estimator below. I think this is probably pretty well for sort of the forest inventory types out there. It's a pretty standard estimator. So in order to integrate the G-Light information with the inventory and the estimation, where we basically leaned on a post-stratified ratio estimator that was actually developed by Anna Ringvall and colleagues at the Swedish University of Agricultural Sciences, I believe that's SLU. And then we also used an approach to classify forest type using the hyperspectral and LiDAR data, kind of both of those approaches to kind of leverage the strong relationship between LiDAR height and biomass, as well as the relationship between the hyperspectral metrics and the forest type. We were using a model-assisted estimator here. So the basic idea behind model-assisted estimation, for those of you that aren't familiar, is basically you can use all of you develop a model, typically using regression or some predictive model. You apply that model over all of your kind of cheaper remote sensing plots, and then you basically use the kind of residual between the difference between the field measured value and your predicted value, where at your field plots to kind of have provide a kind of a bias correction to the predicted value. And then we're also using this estimator is a little bit complex, but it actually has a ratio estimation component to it, which it actually uses the area of the LiDAR strips as in a ratio estimator to increase the precision. So the advantage of a model-assisted estimator is basically it still works in the design-based inferential sort of paradigm. So it's directly comparable to, for example, post-stratified. There's other design-based estimators like the post-stratified estimator. So like I said, it's a little bit complex, but this is the variance estimator for that post-stratified model-assisted estimator that incorporates the G-Light information. Like I said, the ratio estimator uses the area of the G-Light strip as an auxiliary variable and can increase the precision in a multi-stage design. So the variance estimator in this particular estimator has to account for both kind of between strip variability, kind of in that sort of multi-stage or cluster sampling sense, but also accounts for residual variance in the regression model, as well as covariance between stratum level estimates within the strips. And that's what kind of requires the complexity in that variance estimator. In terms of the results, sort of the take home here, this is a comparison. On the left are kind of the standard post-stratified estimates with standard total and standard errors in teragrams. And then on the right is the post-stratified model assisted. So the two right-hand columns show kind of the estimates for using the G-Light information. Kind of the take home here is that when we use that the G-Light assisted, model assisted approach, we get about a 30 to 40% reduction in the standard error, equivalent to about 2.5 times more field plots, which, as you can imagine, with when these field plots are extremely expensive, is a value. We did want to look at, since we're moving into this area in Western Alaska, Western and Northern Alaska, where the field plots are becoming even more expensive. We're actually interested in what happens to the precision when we scale back, when we reduce the sample size even more. So in this case, we scaled back the sample size to a quarter of the original field sample size. And this just shows, the graphic on the left just shows the standard errors for for the different sample sizes. So this type of analysis is giving us some idea of what is sort of the optimal sample size as we move into these more remote areas. What's the optimal field sample sizes that we can use in combination with the G-Lite to achieve the kind of the required or desired level of precision for at least these inventory parameters that are highly correlated with G-Lite. There obviously are inventory parameters that aren't as highly correlated, and we won't see this same relationship. So in terms of kind of the take-homes from this, the precision of the post-stratified model-assisted estimator is much less sensitive to the field sampling intensity than the kind of the standard estimator. It indicates that using this post-stratified model-assisted estimator with the G-Lite with a much sparser FIA grid could be a cost-effective approach in Western Alaska. However, the logistics of implementing this really sparse grid are quite different from the kind of the current logistical situation, and it will require probably different types of helicopters, because it involves different distances to plots and numbers of field crews and these types of things. So there'll be some significant additional planning to be done if we implement this approach. Just a couple more slides here. I also wanted to mention, in terms of kind of future directions for this research, we are collecting this very high resolution, extremely high resolution imagery over every plot, as well as along the strips. So we're quite interested, and this was mentioned by Chris Woodall in his poster presentation yesterday. We're interested in looking at downwoody material measurement using this high resolution imagery. So we think we might get some statistical efficiency out of actually being able to use this 3 centimeter resolution imagery to measure, or at least quantify downwoody material within these plots where we can see it. I also mentioned that we're quite interested in characterizing habitat quality using this high resolution imagery as well. And I know there's been a lot of work in this area in Scandinavia and other places in the world. So we'll be drawing upon that previous work as we kind of dig into this other area of research. And just very, very quickly, a couple more slides. We also are interested in characterizing not only forest and tree biomass and carbon, but also the carbon that's stored in the shrub vegetation. There's significant shrub cover in interior Alaska. This is just an example. This would be considered a non-forest plot or non-forest condition in our FI inventory, because these are shrub species. But we are also interested in using G-Lite data and developing methods to quantify biomass in shrubs and be able to characterize that with the G-Lite imagery over the inventory domain. So let me see. So I just wanted to acknowledge a large group of collaborators that are involved in this study. Some key collaborators include the state of Alaska, as well as many university collaborators, both in the US and elsewhere in the world. So thanks for your attention. I just wanted to also point out that the Tanana FIA database is available online. We cannot actually give out the precise locations of the coordinates, but you can get the data, and if you do need the coordinates for some kind of a study, we can work with you on potentially setting up an agreement to provide the coordinates. And the G-Lite data are also that were collected in Interior Alaska are also available online as well. So thank you.
Thank you very much, Hans. Very interesting work with scaling up NFI data and also finding optimal size, as well as very good that some data is available. I don't see raised hand so far. So then we move to the last but not least presentation by Miroslava Lesiev. Please.
Good morning, good afternoon, everyone.
Yes, we can hear you.
Let me
Good
quickly
morning.
share my screen. Host disabled participant screen sharing.
Oh, no, it's still on.
Host, that's a notification that I'm receiving.
Can you try again?
Should I log out and?
Oh, no.
What should I do? What do you suggest to do me in this case?
Yeah, try. Click on it again, just to make sure you get that message. And if you get that message, then are you comfortable with me sharing my screen with your slides?
Yes, you may share. I did some small changes, but it's fine. They are minor.
Oh, yeah. Yeah. Okay.
They are minor. It's completely fine. So, okay, because unfortunately I cannot somehow, I'm not able to, I'm constantly receiving the message, host disabled participant screen sharing. That's what I'm receiving.
So I'm sorry. Yes. So I'll do
no
that.
problem.
Up. Okay, share. And presentation mode. All right. I'll move that up and that also.
Oh, thank you. So today, good morning or good afternoon, everyone. Today I would like to talk about mapping human impact on forests at global scale, including boreal forests. Interestingly, this work has been started some years ago, and the first steps, these directions were done during our last boreal forest conference that was held at IIASA. During that time, we organized a GeoWiki workshop to collect information of forest drivers, and we have established a very nice collaboration with many of you who participated in this session. Please, next slide. So here you see actually the forest experts with whom we established very close collaboration and who contributed really a lot into this work. And I also would like to acknowledge other people who contributed by helping us to collect the reference data on forest management practices at global scale. Here they are. In total, we had almost 60 people involved in this work. Next slide, please. Our initial motivation was to create a forest management layer for the biodiversity community, since, as we know, land use is very critical information and just having land cover maps is enough. And unfortunately, there is no global land use map available of sufficient quality. Very often such information is outdated or not complete or having unknown quality. And moreover, there is a desperate need for such a product, such a map by many other applications. So we had two objectives in mind. The first objective was actually to build a reference data set on human impact on forest, and the second objective is to use this reference data set to develop the first ever forest management layer based on remote sensing and artificial intelligence. So following the two objectives that we had, our main workflow can be divided into two blocks, basically two main steps. The first step was where we actually invested really lots of resources and efforts is to build a reference data set, which was built with the help of a few crowdsourcing campaigns that we run, and also with a huge contribution by foresters. And in the second step, basically, this is a creation of the final map and the validation. To start with, so a couple of years ago, we organized after the Boreal conference, we organized a workshop internal at IIASA, where we invited the experts from different parts of the world. And here actually we sit down together. That those were times where we could meet in person, could have met in person, and we sit down together and we discuss forest definitions, how to generalize them. We discuss the application interface to collect the data. We can also build the fast subsets as a control point data set that we later on to use in the crowdsourcing campaigns to monitor the quality of the participants, people who were helping us collecting the data. Next one. The crowdsourcing campaigns, so basically were run in 4 stages. We had a campaign for tropical forest, temperate, boreal forest separately, and also we had a campaign on following up campaign on disagreement locations. Next. So here you can see the slide where we have an example of GeoWiki web application. This is a screenshot where the participants basically were asked to do visual interpretation of a blue box and to kind of provide us characteristics of the forest or tree cover they see in this blue box. They had a lot of supplementary information used, which are showed on the next 2 slides. They are listed. For example, the next slide. So they had opportunity to look at the Google Maps, Microsoft Bing Maps, Sentinel imagery, OpenStreetMap. They can also check they're encouraged to check the historical imagery available in Google as desktop application. They check pictures, Google Street View, also historical and divide time series. In addition, Landsat imagery, which was available in Google as desktop application. In addition, they were also using, which is showed in the next slides, they looked at Sentinel time series to check for the recent forest changes, in particular for the year 2015, because our aim, our overall goal was to develop this product, this map for the year 2015. Next slide, please. During the campaign itself lasted 3 months, and we had almost 130 participants. Over this period, we collected classifications for more than 100 unique locations. After the quality check, which we had done internally, we selected 50,000 locations with a very high confidence, and later on we used it for running, for developing our map. Next, please. And in addition to these 50,000 locations, since that was apparently not enough data to create the map, we internally, with the help of the foresters, forest experts, we collected more locations, in total up to 200,000, which you can see the distribution of these locations you can see on this picture. And on the next slide, here I would like, there are classes listed that we provide on our map. The first class for boreal forest, basically I highlighted these 3 classes which are typical for boreal forests. The first one is nature regenerating forests without signs of human activities, which includes also primary forests. This class is a bit broader than Potapov's definitions because it doesn't take into account the minimum mapping unit. And it's broader as primary forests in terms of from ecological point of view, since we were not able to check what happened with those forests, for example, 50 or 100 years ago. So we don't know if there were some human activities. Right now, we cannot track so far away in time. The second class, it's nature regenerating forests with signs of human activity, some logging, clear cuts, or so on. And the third also important class, which is planted forest. We also had other classes such as forest plantations and agroforestry, but these classes were more typical for temperate and tropical forests. Next slide, please. For mapping methodology, we use probably imagery. And as a method, we use random forest and probably images for the year 2015. Next slide, please. So this is a final map that we received, and it's currently available on GeoWiki. You can see by the dark green color, which is, this is actually nature regenerating forest without any signs of human activities. Light green, which is also important because it's nature regenerating forest with signs of human activities, and blue, it's planted forest. Next one, please. We have run the validation global scale and overall accuracy of the map. We received 83%, but we all know that this accuracy varies by classes. For example, by classes, you can see for the forest with low human impact, it will be 80%. I think the lowest was for woody plantations, which is 58%, which is the class typical more for tropical areas. So it's highly rise. It also the accuracy will highly rise spatially. Let's focus more on boreal forest on the next slide. So we have compared our map against the Canadian boreal forest, and for some verification of our results, we found this Canadian intact forests available in Global Forest Watch. This layer is different to the classical Hun-centric cover layer because it includes forests that are affected by natural fires, which is also in line with our definition. So in overall, we found very nice spatial correlation with this product for this class. The next one. The next slide, please. Talking about Russian boreal forests, unfortunately, we don't have an equivalent layer for comparison, and that's the results what we got. And this result has been, I mean, it's maybe surprising for someone that there is so much of dark green or this forest with low human impact in Russia, in Siberia. But this work has been evaluated and approved, validated by Russian experts, including Dmitry, Schepaschenko, and so I would trust here the experts, and it's quite interesting outcome. However, we should know this is also the result for 2015, and to the up-to-date knowledge, I think there are the forest deforestation activities are increasing during the last years in Russia. The next product is the next slide. Talking about European boreal forests, we also struggled to find a map for equivalent. One of maps that we looked at, it was by numbers and all in nature sustainability. It's maps. This is a forest management intensity kind of characterization. And they have forest management intensity classes, not exactly our classes, but I mean, we found that there is definitely correlation in for forests with low human impact, these dark green areas, and in general for a very intensely managed forests, which correspond to our planted forests. But we also have compared this our map against the some FRA statistics for Nordic countries, and we found that we underestimate planted forest in those countries in general. There should be much more. In this class is mainly very much confused with the class number 20, nature regenerated forest with signs of human activities. And this is mainly related to particular mature planted trees, which are very difficult, kind of almost impossible to distinguish from just nature regenerated, mature nature regenerated forests. The next one. And just to give some final remarks, the main map's value is that we managed at global scale, maybe not that much for boreal forests, but at global scale, we managed to, from a remote sensing perspective, to delineate forest and agricultural land use, managed and so-called intact forest, and also different types of plantations. In general, we got a very accurate picture at global scale, continental and regional scales. There are some maps at local scale. That's why we would not recommend this map for some very small scale studies. This is a living map which will be improved over time. It's consistent with the Copernicus land cover at 100-meter resolution. And just to add that the map is currently under the revision in Nature Scientific Data and is almost published and made of open access. Thank you very much for your attention and